So our fourth speaker today is Neena Chandawale from Agnisys. She's based in the USA, California. She's a senior applications engineer. She holds a degree in electrical engineering from the California State University, Sacramento. She's been instrumental in Agnisys' success, leveraging her technical expertise to assist customers in navigating complex challenges and optimizing their systems. And her talk today is creating SVA for formal verification from natural language specifications. Okay, over to you, please, Neena.
Thank you for the introduction, ma'am. Hello, everyone. So identifying and writing correct SVAs is an integral part of formal verification, as you know, but this is challenging due to scarcity of experts who execute this task. So how about creating SVAs from specification written in natural language? I'll be giving an overview on creating system Verilog assertions for formal verifications from natural language specification and share our experience and current state of the art using AI techniques. To start with the webinar, this slide explains the problem we are trying to solve, that is machine translation. What it means is we are trying to convert one language to another. The goal of developing the Agnisys tool, iSpec.ai, is to provide customers with a method for generating system Verilog assertions by articulating their desired requirements in plain English. So we have used large language model to perform this task. Generally, on broader terms, there are two approaches for working on LLM. One is prompt engineering, and another is fine tuning. So let's see these terms in details. Let's consider LLM as a black box. So there are weights and sides of the network. Adjusting these weights is called a fine-tuning process. So in brief, in fine-tuning process, we are making the LLM learn. Whereas in prompt engineering, it utilizes its existing information and it curates a response. There is no learning involved. A fine-tuning process is a pretty computationally intensive task. Couple of months back, there were not many techniques available for this process on consumer hardware. There are extensive researches going on which resulted in this technique called QLoRa, which we have used in iSpec.ai case. Next slide, please, Disha. So what is an LLM? LLM, it's a large language model. It's a neural network which can help you understand, generate, and respond to human-like text. Here, the second bullet explains the architecture used behind the LLM. We specifically use transformer architecture because it is extremely powerful. It can help you identify patterns and sequences. Example, you can visualize a sentence as a sequence of words, and every word in sequence has dependencies on previous words and words forward. This transformer architecture is very powerful in understanding those dependencies in sequence of words. Moving on to the diagram, we have tried explaining where this entire thing fits in general AI space. Basically, it's a shared space. Deep learning is something that is powered by neural network. And LLM is a sub-part of it because there is specific architecture we are working with. So ultimately, it's a neural network. And you see Gen AI here, which is where we are trying to generate something. Next slide, please, Lisa. Okay, this slide dives more into transformer architecture. This architecture was proposed in one of the research papers. In the initial paper proposed, there were two components of the architecture. One is encoder and the other is decoder. Let me explain these components. So consider the input. You can refer the diagram. Consider the input to be translated in encoder. What an encoder does is it ultimately creates embeddings. So it is basically sequence of numbers called as vectors. And these embeddings basically catches the semantic meaning of the input. So this input text goes, some pre-processing steps happen, and then it goes into encoder and embeddings are created. These embeddings are fed to the decoder. Initially, a single word is predicted out of this decoder. Here, DAS is predicted in initial go. In the next timestamp, DAS is refed to the network. Now, DAS is one of the input to the decoder, and encoder embeddings is the other input. These inputs are used to predict the second word, and so on the process continues. The second word is again fed to decoder, and this continues iteratively until it receives the token which says that the sentence has ended. This complete process is single powered by a concept called a self-attention mechanism in transformer architecture. This mechanism enables the model to capture long-range dependencies and contextual relationships within the input data, enhancing its ability to generate coherent and contextually relevant output. The current architecture, though, uses only decoder. Next slide, please. So the next slide explains self-attention mechanism in more details. Here, the input, you can see this diagram on the right side, the input is mentioned, and it is the statement, the animal didn't cross the street because it was too tired. So the tokenization step doesn't necessarily tokenize it into words. There can be subwords as well. Here, if you see, didn't is a word broken into 3 subwords. This is how these like tokens are what the LLM understand, and this is how the input goes. This is what the pre-processing steps are. So the English text is broken like this. Let's consider a word it. The word it has dependencies in the sequence, and it is referring to an animal. If you see the initial blue vector, certain words are highlighted blue, others are white. So more the darker the shade, more important it has. Here, in this case, it is giving importance to street token. Then it is trying to map dependencies with entire statement and not just token previous to it. So what other vectors mean is it is multi-headed attention. At times, a single vector is not able to map all the dependencies. It tries to calculate self-attention with itself too. So if we consider a single-headed attention, there are chances that it might consider itself as the most important token. To cater to this, we considered the multi-headed attention to consider all the possibilities. A 8-headed attention, and every vector is giving different importance to different token. LLMs based on a decoder-only architecture, it utilizes a variation of self-attention, and it is known as casual self-attention. This variant differs from the traditional self-attention in that it only considers tokens that have occurred previously and lacks awareness of the future tokens. Next slide, please. So this slide explains the fine-tuning task. So the transformer architecture is non-trivial and a very big architecture. For small companies, it is impossible to train it on internet-based data. So they use the entire internet is scrapped. What we get is pre-trained LLM for tasks with models for such tasks. This is fine-tuning. So we downstream the model for such tasks. These LLMs are non-trivial, and we don't have ability to train it. They're open source to this LLM. We download these weights and use the networks and fine tune it. This whole process is called transferring. So for achieving the task, we want to figure out a way how our LLM should be. Consider our tool iSpec.ai example. In this tool, we want to prompt the model with an input to output the system Verilog assertions. That is what we call as prompt. So prompt is a user query part, and completion is what desired response you want from the model. So the strategy which we have employed is to enhance this model's performance on our specific task, and it involves instruction fine-tuning. This approach involves training the machine learning model using examples that illustrate how the model should respond to a given query. Next slide, please. So let's move on to next slide. And in this last slide, I explained the fine-tuning of being a non-trivial process. The weight in memory takes floating point 32 bits to store. The method we use to train is that the neural network is we need 3 copies of such weight. So we are at that stage where larger LLMs are taking 300 billion plus weight. And if we take small LLM, typically has like 7 billion such weight. Hence, fine tuning is close to impossible. That is where QLoRa approach comes in. It efficiently does the same task, and it's a combination of 2 techniques, quantization and LoRa. What is quantization? It is building the things in lower memory space. So as I mentioned earlier, for small LLMs, there were 72 billion parameters and 3 copies. So those were like 32 bits, and now they're reduced to 4 bits. So there is a significant reduction in memory usage now. And the next concept, LoRa, it reduces trainable weights by selecting lower ranked matrices like A and B. So it significantly decreases the trainable parameter. The pre-trained model weight remains frozen while adapter matrices train on the fine-tuning dataset. Next slide, please. So this slide shows Agnisys tool iSpec.ai, and this tool provides comprehensive functionality. It encompasses both like English to SVA and SVA to English generation capabilities. And it will be available on all the editors provided by Agnisys tool, including Word, Excel, IDS-NG, which is Agnisys cross-platform GUI. This was all about the tool. Thank you so much.
Thank you very much, Neena. One question is, I mean, how accurate is the SVA that's being generated? Do you have to do any editing on it, or can it be used directly? Is it syntactically correct in your experience?
So it can be used directly. If you write like in English, the result which you get in iSpec.ai, it is perfectly fine, and it can be used directly in the formal verification. The assertions can be used directly.
In both formal and simulation, I guess, yeah.
Yes.
Okay. Okay. And can you extend this to beyond assertions? Can you use this for coverage? Can you use this for tests, for example?
Currently, it is just used for assertions, like generating system Verilog assertions from English language.
Okay, but could it be used? I guess you haven't used it, but could it be used beyond that?
I think for now it's restricted just for assertions.
Okay.
Yeah.
And for those who aren't aware, we had this previously as similar presentations on this. So I think there's a lot of similar companies using this type of technology to generate both SVA, as Neena's presented there, and other types of technologies. But we'll put the link to those talks from previous events when we send you the email for this. And one question coming line from Darren Galpin: how dependent is this process on the quality of the English? For example, if there's strange syntax in the specification, can your tool still understand that?
So what the tool expects is like normal English, what we talk. I mean, the typos are okay, but the normal plain English is understandable by the tool, and it can generate the correct result.
Okay, and what I think you're saying is it's reasonably tolerant to spelling mistakes, etc. Correct?
Yeah.
Okay. Okay. Thank you very much, Neena. That's the final presentation today. I will just share my closing slides so we can close out the event today. Okay, quickly. Can you see my screen or not yet?
No, Mike, I can't see your screen.
Visible now?
It's loading. Yeah, now I can see it. Please go ahead.
Okay. So just a thank you today for participating in DV Club Europe. I hope you found it useful. Some good examples of applications of formal verification, as well as a couple of tool vendor presentations as well. Thank you to our sponsor, Agnisys, Cadence, Breca, Synopsys. Thank you for TESOL for hosting this event as well. These slides and recordings will be put on the formal on our DV Club page. On that link there, you will be sent that link. The PDFs go up pretty quickly, if allowed. Sometimes the speaker doesn't allow us to put the PDF up, in which case they won't go up. But if we've got approval, the PDF will go up likely today or tomorrow, and the recording will go up in a few days' time. You'll be sent an email to notify you on that. If you've got other ideas that you'd like to see, suggestions for topics, just let me know. And some of the things that are coming up. On the 3rd of September, we've got another low power verification. Our next DV Club Europe, which is on low power verification. Our one in November is still TBD. We're running in India as well. On the 28th of May, we are running showing my design verification is ISO 26262 compliant. And then in July, we're going to run something on chiplet-based systems. That is physical event in Bangalore, but also broadcast. And of course, we've got our two physical events coming up on the 18th of June in Reading University, Verification Futures, and then we're running our second Verification Futures in the US at Austin. Okay. So thank you, everybody, for today. Thank you for joining, and hope to see you at one of our future events. Thank you. Thank you, Disha.
Thank you, Mike. Thank you, everyone.
Thank you.
Thank you.
Thank you all.